So here for the first part of our quarter, we're going to start with heat. And so we're mainly talking about what heat is and how heat moves. So to start that off, we have heat transfer notes part 1 here. So everything in yellow needs to be included and answered in your notebook. So if you want to do this on a computer too, that could be fine, but make sure that you're not just copying and pasting, you're putting your ideas in. That'll help you learn a lot better. And so you're going to need to submit your answers, the things in yellow, in your notebook for grading. So make sure we're putting those in there. All right, so these are 10 questions we're going to use that we're going to answer. What is heat? How is heat measured? How do you convert different units of heat? What is temperature? Different types of the way we measure temperature. And then how does heat move? So hopefully when we get through this, you'll get some good ideas here. So this first one, we got a picture here, and we want to think about what is this showing? And you can hopefully hear this is represents a radiator. Maybe some of you have these in your house, or you've seen them in other people's houses or apartments. So we have those big metal tubes on the wall, and they actually have hot water going through them, and that hot water in those tubes warms up the air. And then this is actually showing how that hot air actually moves up and circulates through the room. So here we have an example of hot air that's rising up in the room. And same way over here, we have a window. Windows are usually cold. If you feel them right now outside, the window will feel colder than the wall. They're not as well insulated. And you can see here how that cold window cools down the air that's next to it, and that cold air gets more dense and sinks and makes like a current of air running through the floor. So if you put your hand underneath a window or along the floor underneath the window, a lot of times you can feel this cold air running through your house, especially in I got an old house. It's very drafty. So this is showing how heat can move through air that's moving. So a lot of times people say heat rises. Heat doesn't rise, but hot air rises and cool air tends to sink, and that can carry heat with it. So hopefully that gives you a picture of what's happening. We have this idea of what is heat. So basically, heat's the energy of motion. All molecules, everything that we're made of, has little atoms that are bonded together. And when these atoms are bonded together, they don't just sit still. They kind of shake and move around a little bit. And the more energy we give them, the more heat energy, the faster they'll shake around and the faster they'll move. So we add heat energy to objects. Those objects speed up. And then on a molecular level, we can see them going faster and faster. Same way, if we take heat away from a molecule, it'll slow down. And that's why you can think about water freezing. As those water molecules slow down, as we take heat out of them and cool them off, eventually they start to move so slowly that they can lock together and form a solid like ice. And many materials do that. We call that a phase transfer. When the molecule speed changes and they go from a solid or a liquid to a gas. We'll talk about that more in a little bit. How is heat measured? Well, heat is a type of energy and actually measured in joules. Just like we've been measuring electricity, electrical energy, just like we measured work and power, we use joules, and that can be used for heat too. We also measure heat with calories. Here we have a lowercase c calorie. There's a difference here. This is the metric unit of heat, calories, and it's defined as enough energy. 1 calorie is enough energy to make 1 gram of water go up by 1 degree Celsius. So that's the definition of a small c calorie. We also see calories when we look at food containers, but those are actually capital C calories. They're different. And a capital C calorie is actually a kilocalorie, and it's equal to 1,000 small c calories. So even though you don't see the K for kilocalorie when you look at food, 1 calorie is a small amount of energy. So when they look at your Rice Krispies, they actually measure it in capital C calories, or which are 1,000 little c calories. And we're going to actually use that to figure out how much energy is in food and what it can do. There's another unit here, the British thermal unit. Sometimes you'll see that on a furnace if you look in your basement. These are used relatively large amounts of heat, but that's used in. And that's also based on this whole idea of changing how we change the temperature of substance. So 1 BTU is the amount of energy needed to heat 1 pound of water, 1 degree Fahrenheit. So a pound of water is a lot bigger than a gram. So a BTU is a lot bigger than a calorie. All right, to get used to those units a little bit, let's think about this. How much could a Big Mac heat up Ariana? All right, so we can figure this out. I'm going to write on the screen here a little bit. If we know how much Ariana weighs, so we'll assume she weighs 55 kilograms, and that she's made entirely out of water, we can figure out how much heat goes in there. And so we're thinking about a Big Mac. 1 Big Mac actually has 563 big C calories, which means it's 563,000 little c calories. Uh-oh, we got an error here. 55 kilograms is equal to 55,000 grams. And so we need 55,000 little c calories to heat up Ariana 1 degree C. So 55,000 little c calories can heat up 1 degree C, because each one of her grams, that's how much a kilogram is, right? Kilo means 1,000. So there's 55,000 grams of Ariana. And to heat her up 1 degree, each one of those grams would need 1 little c calorie. So if we think we got 563,000 little c calories in a Big Mac, and we need to heat up Ariana, we need 55,000 calories for 1 degree. Well, we got to see how many times does 55,000 fit into 563,000. So you can see here it's going to be a little bit more than 10 degrees, and we could do that on a calculator here. So if we did 563,000 divided by 55,000, we're going to get a little bit more than 10. So one Big Mac could actually, if we put all this energy in the food, we burned it and put it into Ariana Grande, like she's a big pot of water, we'd actually heat her up about 10 degrees Celsius. Now, a Celsius degree is bigger than a Fahrenheit degree, so that would be about 18 degrees Fahrenheit that we could raise our temperature. So think about that. When you eat a Big Mac, there's enough energy in there to raise your whole body temperature about 18 degrees Fahrenheit. So I think that's kind of cool. So kind of try to get those calculations in your notebook. We'll see what you got. We also want to do a conversion here. Convert BTU into joules. So 1 BTU is 1,055 joules. And we want to think about how to do that. Well, there's a video here you can watch if you're stuck. But basically, it's one long unit conversion. So if we remember that 1 BTU is enough energy to heat up 1 pound, 1 degree Fahrenheit, we need to convert that. So 1 BTU is equal to the heat of 1 pound, 1 degree. So it can heat up 1 pound of water, 1 degree Fahrenheit. And so we need to do some conversion factors to change that into pounds needs to go to grams, and Fahrenheit needs to go to Celsius. So you guys can watch that other video to check that out. We'll keep this one a little bit shorter. Okay, the next thought is, what is temperature? Temperature actually measures how fast molecules are moving. So we can look at it here. If I can turn off this little clip. All right, I think I got it out of the way. So now we can see at 0 degrees C, these molecules are not moving very fast. 0 degrees Kelvin. Kelvin is another way we measure temperature. We'll get to that in a bit. But at higher temperatures, they move faster. Another thing we can look at is friction can heat up the objects. So you can click on this link. You can go to this video here, and you can see what happens when we move these books around. So if we shake these books together, you can see how that raises their temperature. Eventually it slows down because these vibrating atoms here, eventually that energy spreads out to the rest of the book and that heat spreads throughout. But if we just rub the surface together, you can see how that makes those molecules vibrate more and more. And that higher temperature that we could feel is we're actually feeling how fast those molecules are moving. All right. So that's temperature. It's the speed the molecules are moving at. And this brings this idea, if molecules can move faster and faster, they can also move slower and slower. And if you go slow enough, eventually you stop. You can't go slower than stopped. And so the temperature when all molecular motion stops is actually called absolute zero. It's as cold as anything can get. And it is actually negative 540 Fahrenheit. You can't go colder than negative 540 Fahrenheit because that's when motion stops. So that's pretty cold. And we can talk about more of that too later. Okay, how is temperature measured? Well, we have basically the Fahrenheit and the Celsius scale. We're used to the Fahrenheit scale in the United States. The rest of the world, almost all the rest of the world, uses the Celsius scale. The Celsius scale is nice because it's based on water. So the boiling point, 100 degrees Celsius is the boiling point of water, and 0 degrees Celsius is the freezing point of water. Of course, for Fahrenheit, that corresponds to freezing is at 32 degrees Fahrenheit, and boiling is at 212 degrees Fahrenheit. These are both linear scales. That means that 1 degree is the same amount in each scale. They go up, they keep going up the same. And we can convert them back and forth. So 1 Celsius degree, if your temperature goes up by 1 degree Celsius, you're actually going up by 1.8 degrees Fahrenheit. Now remember, this is a change. All right, so if you change by 1 degree Celsius, you change by 1.8 degrees Fahrenheit. That doesn't mean that 1 degree C is the same as 1.8. And we can see that 1 degree C is actually over here more like 33 degrees Fahrenheit. But if we're talking about change, how much the temperature is rising or lowering, then we can say there's a direct correlation. 1 degree change in Celsius is a 1.8 degree change in Fahrenheit. And they give us a formula here we can convert back and forth. So if you have the Celsius temperature and you multiply it by 9/5, and then you add 32 to it, that will convert it to a Fahrenheit temperature. All right. Let's go here. The next part here is we want to think about how can we rearrange that then to go back and forth. So this formula is set up. If you know the Celsius temperature, we can turn to Fahrenheit. And we want to derive a formula, that means show where it comes from, going the other way. So here we have Fahrenheit temperature by itself, because that's what we'll end up with. Let's rearrange that to get the Celsius temperature by itself. Now this is kind of like an onion. We have to unpeel the layers. So if you're going to do this math over here, first you would multiply and then you would add. So if we're going to undo that, first we're going to subtract 32 from both sides. And we're going to get degrees Fahrenheit minus 32 is equal to 1.8 times degrees Celsius, because 32 gets canceled out by subtracting. And now we need to get rid of the 1.8, so we're going to divide both sides by 1.8. And that'll cancel out the 1.8. And we're going to be left with, if we take the Fahrenheit temperature, subtract 32 from it, and then divide the whole thing by 1.8, that will give us the temperatures in degrees C. So that would be our conversion for that. The next step here is we're actually going to convert back and forth. So you need to look up these temperatures on the previous slides. The freezing point of water, we said it was 32 degrees Fahrenheit, 2 degrees Celsius. And then we need to convert back and forth. So if you start with the Fahrenheit degree, then you're going to use the formula we just did. You're going to subtract 32 from it and then divide by 1.8, and that'll turn into Celsius. If you have the Celsius temperature, we need to do the opposite. We need to multiply by 1.8 and then add 32. Just like our formula says here. So we're going to multiply by 9/5, which is the same as 1.8, and then add 32 to it. And that will convert us back to the Fahrenheit value from dry ice. So you guys can go back and forth and fill out that table. The last couple that we have here, let me see. Uh-oh. Oh, good. Still recording. Got scared. All right. The last section we have here is how does heat move? And so there's 3 ways here. We have conduction, when heat moves through a solid, convection, when heat moves through a moving fluid like hot air, and radiation, where heat actually moves through infrared or different types of radiation. So if we look at this, here's conduction. If you vibrate one side of a molecule here by adding heat to it with this flame, then it's going to shake the molecules next to it and shake the molecules next to it, and that shaking energy will be transferred all the way down the material. This is called conduction, when the energy is transferred within a solid material. All right, we have another one here, convection. Convection is when you have a moving fluid. Our most common example is air, but you can have other fluids, anything that flows. Water, oil, steam are all different ways that heat can move in a fluid because the fluid flows. So here's an example. We have a heater. Cold air gets brought in the bottom. It gets heated up by the burning logs. And then that hot air travels up and out of the furnace. And as this hot air moves, it carries the heat with it. A good example of this would be a hair dryer. The hair goes into your hair dryer, and then it gets warmed up. And then it gets blown out and carries the heat with it. All right, I got my picture back. Okay, here's a good example of the way different heat's transferred. So hopefully you guys have seen this, or you've done this in your house, or you've seen this cooking. You could have a pan. Which pan would be hotter to hold your hand over? So you could hold your hand over the boiling water, which is at 212 degrees Fahrenheit, or you could hold your hand over a pan of hot oil, and oil can actually be much hotter, 350 degrees Fahrenheit. And probably most of you know that the hand feels hotter over the boiling water than it does over the oil. And why is that if the oil is hotter? Well, the idea is that when you have boiling water, it's creating steam, and that steam in those bubbles is moving up, and it brings that heat to your hand. So even though that steam is not as hot as the oil, the steam can move and bring the heat to you. Another example of that is, why does it feel hotter to hold your hand over the hot oil after the food is added? So everyone should, well, hopefully you've seen, when you add that chicken in there, all of a sudden it gets really hot to hold your hand over it. And that's because there's water inside that chicken that actually boils when it gets put in the hot oil. And that boiling water makes the steam that makes all those bubbles in the oil. And when that steam goes up, it can actually be very hot, hotter than boiling, because it can be heated up to 350 degrees at the temperature of the oil. And then that hot steam can bring to your hand, and that can be very hot and burn you very easily. So you got to be careful with that. We got almost done here. We got 2 questions left. One is, how does heat move through radiation? And this is this idea that all objects give off radiation. And so sometimes you might be used to the infrared pictures or the heat image pictures, and what they're actually showing you is the thermal energy coming off. So even you can feel your own face. If you put your hand close to your face, not touching it, but just close, it'll start to feel warm. And that's because what you're actually doing is you're feeling that radiation that's coming off from your own face. So it's kind of fun. So hot objects give off more radiation than cold objects. And if you receive more radiation than you give off, you'll start to warm up. So an example of this lady sun tanning out here, she's giving off radiation, but she's getting more radiation from the sun than she's losing through her own infrared radiation that tends to heat her up. So we can look at that a little bit. Here's some examples. A lot of times we call this red hot, this old electrical burner. As it heats up, it starts giving off more and more energy. And as it gets to higher and higher energy, it can give off higher energy light waves. So infrared are something that you can give off with your skin. When you get it hotter, several hundred degrees, things start to glow. And you can see down here, at 600 degrees Celsius, things start glowing red, and then they get brighter and brighter as you get hotter and hotter, and you're giving off more higher energy wavelengths, more greens and blue light. And if you put all those colors together, you get white hot. All right, the last one here, we got this idea of a microwave. Microwaves also give off radiation, and they give off microwave radiation, which is actually a longer wavelength than infrared. So inside here, your microwave doesn't get hot, but that energy, that microwave energy, gets absorbed by the food and heats it up. So the turkey, as it gets hot, gives off infrared radiation, which you can see with the little arrows, but it's getting more energy in through the microwave, so overall that turkey gets hotter. All right, so the last one here is, what direction does heat move? And everyone wants to say heat moves up, and that is not what we want to say. So hot air can move up, but heat can move in any direction. And we have here from conduction, here the conduction, the heat's moving sideways. Here's an example of convection, where the heat was moving up with the hot air. But then we have radiation over here, which can move in any direction. So heat can move in any direction. Natural convection, when we have hot air rising, that can go up. But convection can be any direction, like a hairdryer. Hairdryer can blow up, down, sideways. So hot air can move in any direction. But we do know that heat always moves from high temperatures to low temperatures. So the answer we want is heat always moves from hot to cold. That's the good answer for you. All right, so I hope you guys get this down in your notebook and then turn it in, and we'll get you some grades in the grade book. Good job.